We continue. And essentially the study extent of a given reaction, and as pointed out yesterday, when a reaction proceeds as a function of time, we typically monitor changes in concentration versus time. Now, one of the mental experiments that I ask you to think about in dealing with this for reactants going to products and ultimately reaching an equilibrium is to think of the reactants as in a horse race, and think of the reactants as being in the gates of a horse race before the start of that race. And so we're saying no products have been generated. Then I ask you to open the gates, let the reaction run, so to speak. And we noted a trend where the reactants decrease in concentration, and of course the products increase in concentration and reach that zero slope point somewhere in time like that. And we learned this is extent of reaction through those points, and then we apply new concepts once we pass that point, the equilibrium point, and call it the equilibrium region. And that runs from here to wherever how far else you want to go. But in here, the law of mass action dominates, which is the rate forward reaction equals the rate in reverse. So this leads us to writing empirical reaction for a forward reaction and an empirical relationship for the reverse reaction, writing the rate laws and setting them equal to one another. So as the rate forward equals rate reverse, what this ultimately gives us is the equilibrium constant. KEQ, which is defined by the product of the concentration of the products divided by the product of the concentration of the reactants. So essentially you just think products over reactants raised to the coefficient powers, where A and B are coefficients of the balanced equation. And so this is what kind of started us off yesterday. Whereby we applied what we call the ICE table. The ICE table is, I'll just repeat one of the problems we did again. The ICE table is used to define, well, if you start a reaction, what are the concentrations at equilibrium? We did one real quickly, PCl5 equilibrium. These are all gases, PCl3 plus Cl2. And we set this up as a CI, change in C and C at equilibrium. And we'll do this several times today, just doing a review. This is I, C change, and E equilibrium, ICE table. So here's one problem, gave us 2.50 mole to start, and we recalled that if the reaction hasn't started, there's no products. Now open the gate and let the reaction run, so to speak. Now the coefficients define the change. Since all of them have a balanced equation of 1 in coefficient, 1 mole each, then the reactants going down in concentration, we'll use a minus X, and products, we use a plus X. The algebraic sum between the start and the change will give us the equilibrium. Now, one of the problems gave us X, 0.338 mole. Well, if this is X also, it's equal to 0.338 mole. And then we have 2 equals 2.5 minus 0.338, and that's in moles, and whatever that comes out to be. And so those are your equilibrium moles in that context. Is everybody following me? And, this is exactly what we did at the end of class. I know everybody was tired then. But did you follow me okay up to this point in this context? Any questions? Okay. So this is really where we arrived in, but before we had to drop out yesterday. Now, if you'll get your worksheet, and I want to look at the problem 1434. Now, it pushes beyond just getting moles. So we're looking, I need to go through this one and emphasize these 3 points in this question, because that is the focal point of just gobs of questions in the future. Okay. Problem 1434 starts out, says methanol, formerly known as wood alcohol, is manufactured commercially in the following process. Now, you're going to be setting up an ice table, so just take your reaction, move it over kind of in the center of your workspace. Like that. So, having generated this, we want to indicate initially, which is your initial change in equilibrium, and I like to put them in this context, CEQ, concentrations values. Okay, so the problem goes on, and you fill this in as you read problem relative to what the reaction is doing. A 1.5 liter vessel was filled with 0.15 mole of carbon monoxide and 0.3 mole of hydrogen gas. So we want to jot those here. That's 0.15 mole and 0.30 mole. In that position, when this mixture came to equilibrium at 500 Kelvin, the vessel contained 0.1187 moles of carbon monoxide. So we're at 0.1187 mole of the carbon monoxide. Okay, now what you do is, as how many moles of each substance were in the vessel at equilibrium or anywhere else in here. Well, the moles of product, of course, hasn't started yet. So we'll just put 0 moles there just as an indicator. Change in concentration refers to plus and minus x's that you would apply relative to the coefficients. On the left side, of course, the products are generated from the reactant, so the reactants are going to go down in concentration. So this would have to be listed as a minus x of the carbon monoxide, minus 2x because it has a 2 coefficient, and 1x would be increased for the methanol. The algebraic sum of the initial and change gives you the equilibrium concentration. So this would be 0.3 minus 2x, and this would be 0 plus x, or simply x. Now, we can use the column 1 here for CO to determine what x is, and it's a little algebra problem. So that'd be 0.15 minus x is to give us 0.1187. And of course, X now is 0.15 minus 0.1187, and units are moles, if our mole. Oh, 0313. So that would be the X value in here, so we would substitute 0313 for X. Let's see if I can get it in here. Yeah, it's making a mess. 2 times whatever, 0.0313. And so what is that? Times 2 is that negative plus 0.3. 0.2374 mole. Mole right there. Of course, X is 0.0313 mole. Okay, so I think everybody has seen all of this. Everybody good so far? All right. Now, go on. What's the concentration of each substance in moles per liter? Now, we're really not interested in the concentrations up here in the ice in the initial, unless the problem specifically asks you for it, or the change region. It's the equilibrium region that we're interested in. So I'm going to come down here, concentration, just put brackets on this, and we're going to lose the equation. I mean, CO gas plus 2H2 gas, equilibrium with CH3OH is a gas. We'll come over here, and we'll put molar concentrations at equilibrium. And it's very important that you're able to do this. Now, they gave us in a 1,500 milliliter or liters? I think it's milliliter. No, it's 1.5. It's 1,500 mils, but it is 1.5 liters. Well, we know molarity is moles over volume in liters, so we know what our moles are. So for the carbon monoxide, 0.1187 over 1.5, and that's molar. And then for the hydrogen, we have a 0.2374 over 1.5. That's in molar terms now. And then we have a 0.0313 over 1.5, and that's in molar. Like that. So punching them in the calculator. Oh, 0.079 molar. .158 molar, and .021 molar. Okay, so those are your molar concentrations of each one. Now, what's important about this is it goes on to the next question, as what is the equilibrium constant. When you calculate equilibrium constant, you have to use molar values, because that's what the equilibrium expression is based on, change in concentrations. And concentration refers to moles per liter, not just moles. Moles is simply, not to minimize its importance, but it's a mass number. It's not a concentration number. So when you need to calculate the equilibrium constant for the problem, in this case everything's gas, so we'll call it a KC expression, molar concentration. is products over reactants, and so we have CH3OH in moles per liter divided by carbon monoxide in moles per liter and hydrogen gas in moles per liter, but you have to square it because it has a coefficient of 2. And so we extract the appropriate numbers. Methanol is 0.021, and you could drop the units because the magnitude is the only thing of significance. Now, maybe the test will ask you, well, what are the units of this yada-yada? But it really isn't significant relative to defining the question about, or answering questions about the reaction. Okay, so that would be to the first power divided by CO, and that is 0.079 molar. And make it look right. Hydrogen is 0.158, and we need to square that. And when we complete that calculation, we have the K value. And I got a 10.7. Okay, and so 10.7 says you have a mixture of reactants and products, but the concentration is concentration comparison between reactants and products. You have more products than you do reactants because it's a number greater than 1. If you have a fractional K value, it means you have more reactants than products in that equilibrium. Now, one that's kind of interesting, what if Kc equals 1? What does that mean about your concentrations? Well, it doesn't mean that all of the concentrations are the same on the reactant and product side, but what it does is it says the product of the concentrations of products equals raised to the power A or what A and B or whatever the coefficients are is equal to the product of the concentration of reactants raised to whatever coefficient exponents it has. And when you write out your exponents, it's the product of CO and H squared would equal the product of this, well, there's nothing else, whatever the concentrations is. But it's not the concentrations totals here do not necessarily equal that one. They're not the same. It's this expression where the numerator equals the denominator. Well, the numerator and denominator may be mathematically dependent on products and exponents and you name it. So be careful there if a question pops up where it deals with Kc. And a lot of times they'll give you the concentrations of, say, 3 in a K value, and you have to calculate that other one. And you just set them equal to each other and solve for the unknown. And so that's kind of an off-the-cuff type problem, but I think you understand what I'm saying. So heterogeneous equilibrium has one fundamental factoid that you need to be aware of. It's very simple, but let me show you what the deal is. Okay, the reaction I want to use is 3Fe as a solid plus 4H2O gas or water gas, steam, however you want to look at it, in equilibrium with a weird form of iron oxide, and it's a solid, and the outcome is hydrogen gas, 4 moles of hydrogen gas. Now, if we wrote the complete equilibrium expression in this reaction, total EQ, then we would have certainly this expression, with power. Now, it can be shown by experiment primarily that the solids, and if you have a reaction with these liquids in combination with gas phase, the solids and liquids do not affect the equilibrium values in that reaction. They are exclusively dependent upon the gas phase concentrations, gas phase component concentrations. So the solids, or if liquids, are ignored. And so the Kc, now that everything's gas phase, we can use Kc terminology, and so the appropriate measurements are made around gas phase concentrations of hydrogen gas and steam or water gas. Like this. So anytime you have a reaction that has mixed states of existence, ignore solids and liquids and write your expression in terms of the gas phase. Example is evaporation of water, for example, or condensation. I'll use condensation because it gives a reciprocal factor. So if we had H2O in a gas phase and we're condensing it at an equilibrium to H2O as a liquid, and if you ignored the liquid phase, then you would put 1 as a product side, and your Kc expression would be 1 over H2O as a gas, and that would be your appropriate equilibrium expression. You don't have anything on the product side, so you use the reciprocal of the concentration of the water vapor. Okay, the other example is if you have two reactions you're adding together, or they're called simultaneous reactions. They're both running at the same time. In general, the reaction system is referred to as simultaneous reactions. And what we do is adding the simultaneous reactions together gives what is called a net reaction. Sum of reactions gives a net reaction. And it is the net reaction that we generate the equilibrium expression in and the equilibrium constant. An example I want to show you is what we call a H2S scrubber reaction used in the oil business, because a lot of the production has hydrogen sulfide and carbon monoxide mixed up in it, and those are certainly deadly gases, and so it's not a good thing to let those out in the atmosphere. So they use what is called a scrubber reaction, and it is typically a simultaneous reaction between the following. We call this reaction 1, and it's carbon monoxide gas plus hydrogen gas in equilibrium with methane gas and water gas. And we call K1. So this is equilibrium constant 1 is 3.92. Okay? Then reaction 2 is methane plus 2H2S gas goes to CS2 carbon disulfide gas plus 4H2 gas like this, and you have K2 as 3.3 times 10 to the let me put it down here, 3.3 times 10 to the fourth. So it's a very good reaction to produce those particular products. It reacts well in shifting the reaction to that product side. Now, if we added these reactions together, what would we get? Let me be sure I've got the systems, all the details. Okay, we want to add these two reactions together to get reaction 3. And of course, this is what I'll refer to in other chapters that do the same thing as a net reaction. And it just means we're adding together a couple of reactions. Well, when we look at the reactant and product sides, we see methane will drop out 3 out of 4 hydrogen, so that becomes a 1 or a coefficient of 1 on that term right there. And I think that's everything. So on the reactant side, we have CO as a gas plus 2H2S as a gas and the reactants. And that's converted to carbon disulfide, which is a gas, and that can be easily condensed into liquid phase, and that's used widely in industry for other products. And we have H2O gas plus H2 gas. Okay, so there's your equilibrium expression, equilibrium equation that we need to have a K value for. Well, for adding reactions, the K net is always the product of the individual K values. K1 times K2 that you're adding together. And if you had 3, you'd add 3 Ks. In the energy section, when you get to it, I'll show you how to add reactions together. And some of those problems have 3 reactions you're adding together. Well, they would also have 3 K values. Okay, so we multiply the 2 together. The net would certainly be K3 in this case, which would be K1 times K2, 3.92 times 3.3 times 10 to the 4th, which is equal to 1.3 times 10 to the 5th. So this is the effect of adding those 2 reactions, and others will do the same thing. Problems may give you concentrations in the reactions, individual reactions, and you'll add them together and then apply the net reaction and get the concentrations. And the equilibrium expression now, K net for K3, let me do it that way, K net, so it didn't confuse somebody later. K3 is the product of the concentrations of products divided by the product concentration of reactants raised to the appropriate coefficient values of the net reaction. So our expression would be CS2 as a gas times water gas and hydrogen gas in the net reaction divided by carbon monoxide gas divided by hydrogen sulfide gas squared. So there is your net reaction, and all of that is equal to 1.3 times 10 to the 5th. And if you're given any of those concentrations, say part of the reaction concentrations, how much of the yield will you get? You can use this expression to get those carbon disulfide yields right here. Maybe given the gas and the hydrogen, So you'll be given those concentrations, except say for one, and you plug it into this expression and solve for the unknown. Okay, now we want to look at another issue with equilibrium constants. It's fractions and multiples of one reaction going to another reaction with different concentration levels. And I'll show you what I'm saying. Now, one problem in the handout at the bottom, it says the equilibrium, that's problem 1438 in your worksheet. The equilibrium constant expression for a gas is given by this, Kc is equal to CO2 to the third power, H2O to the fourth power, C3H8, and O2 to the fifth. And they want to know, write the balanced chemical equation corresponding. Well, we've done that, but what I want you to do is write one for the reverse reaction that you divide by 2. So you have to write the reaction first. So products over reactants would be C3H8 plus 5O2, all of its gas, in equilibrium with CO2 3 plus 4H2O. Now what I want you to do is take this and reverse it and divide it by 2. Okay? So reverse and divide by 2. So we're going to go 3/2 CO2 plus 2 H2O will now be in equilibrium with 1/2 C3H8 plus 5/2 O2. Now write me the equilibrium expression for that. Okay. So when you write this one, say reaction 1 versus reaction 2, what do you get? Okay, reaction 1 gives a K1 to equal CO2, as we've shown up here, cubed, and H2O to the fourth power, and divided by C3H8 and O2 to the fifth. Now let's say that equilibrium constant is 68. It comes out, whatever it is, it's 68. What is the equilibrium constant for when you reverse the reaction divided by 2? Okay? What you cannot do is take the reciprocal and divide that by 2. I'll show you. If I took that and divided by 2, that's 34, and then the reciprocal of 34, let's see, 68 goes to 1 over 68 divided by 2, that's 1 over 34, and that gives you a number, okay? That's what I'm trying to make a point here about what you can and can't do with something like this. Okay, so 34 reciprocal is 0.0294, 0.0294. If you did the same thing to the equilibrium number that you did to the reaction, okay? But it turns out you can't do that. What you have to do is you have to write your equilibrium expression for K1 and then the equilibrium expression for K2 and ask yourself, how did it get there? How did I go from 1 to 2? And then you apply it to that 68 in this case. So K2 in this case would be C3H8 to the 1/2 power. Okay, that's the way we write them. O2 to the 5/2 power divided by CO2 to the 3/2 power and H2O, H2O squared. Now look at K1 and K2. how would you go from K1 to K2? Did I get that right? I got it upside, yeah, I flipped it over. It's the reciprocal right here. So what did I do to get to from here to here? Could it be something like 1 over the square root of K1? You look at it, Okay? So if you flip this back over, and if you had this on top, the CO3, 3 halves, and H2, okay? And then look up here at the original, yeah, here, where's the CO, yeah, here and here. What did you do? You cut them in half, the coefficients in half, but how do you get to this? That 3 halves is a square root factor, isn't it? Of square root of that, of whatever you write in this expression. If I want CO2 to go to 3 halves power, how would I get it there? I don't divide by 2, I'd have to take square root, wouldn't it? Y'all need to brush up on your math on this. Because you cannot do this just because I made the equation change. Because if you take K2 to be 1 over the square root of K1, that would be 1 over 68, the square root, and that don't equal that number. So 68 square root and reciprocal is 0.121. That's what you should be getting. Okay, so you have to, what I tell you to do, when you get the original equation, we've got some more we can work, and I'm sure you can find them in the practice exam. Write the original equation and its equilibrium expression. Now, whatever they give you for the second equation, you have to write the equilibrium equation for that, expression for that. And look how they change, how you go from first one to the second one. And once you see how that's changed, then you apply it to the first as to how it's done. Usually it's a reciprocal square root or reciprocal squared or K1 squared or something like that. And in the context of the type of problems you're going to have to deal with. Okay, it says the equilibrium constant expression is given Kc to equal NO2 to the 4th power and O2 to the 1st power divided by N2O5. Okay, what's the equilibrium constant expression if you cut the reaction in half and then reverse it? Well, first you got to write the reaction for the first K value. We'll call this KC1. Let me move that over. KC1 is equal to that number. So this is product over reactant, so our reaction's N2O5. 2 in front of that, it's going to be in the gas phase. And then we'd have NO2, 4, and those are in the gas phase. And oxygen, 1, O2 gas, like that. Now, the question asks us what happens to the equilibrium expression if we reverse it and cut it in half. So, reaction 2 would be half of 4, it's 2NO2 in gas form, plus 1/2 O2 in gas form, equilibrium of N2O5 in gas form. So there's your reaction number 2 reversed and put in half. So KC2 now is products over reactants. So that'd be N2O5 as a gas to the 1st power, and NO2 gas, it look like a gas, squared and O2 to the 1/2 power. Like that. Now, compare K1 and K2 and ask yourself, what can I do to K1 to get to K2? These look like square root numbers relative to those exponents in the K1, right? Can you see that through that, guys? And it's a reciprocal. So what's the relationship between KC1 and KC2? Okay, KC2 is equal to 1 over the square root of KC1. And problems will give you, say, 15 for a value. Well, if you come down here, it's the square root of 15, and whatever that comes out in your calculator. I get 0.26. Okay, so it shows that the cutting in half and reversing reaction changes kinetics quite a bit, or equilibrium position quite a bit. It would not produce as much product in this format, number 2, as it would in the first one, hypothetical, if that happens to be the numbers. Everybody okay on this? Okay, please take a second look at it, because there are a couple on the exam, but just remember to compare the equilibrium expressions and ask yourself, how did I get from A to B, so to speak. So let's say you're given that reaction. Well, this question asks you to write the K value in terms of Kp, which is referring to partial pressure. So each one of these as a gas can exert a partial pressure, which is by definition, is the pressure exerted by that gas in contact with this pure condensed phase. Like if you had pure water making a vapor over the water, it has a vapor pressure, but it's in contact with this pure condensed phase, and that's by definition vapor pressure. So you can write this in terms of products over reactants in the same way that we use molar concentration values, but we have to call it a Kp value. And so that'd be the partial pressure, and the way that's written is like this. And don't use brackets, we just use parentheses like that. So you see the partial pressure of methane gas is there, and then times the partial pressure of hydrogen sulfide as a gas. Well, I should put the G down here. G down here. And that one has a coefficient of 2, so we have to square that term. And then we have partial pressure of CS2 gas to the first power, and hydrogen gas raised to the fourth power, fourth power, like that. The relationship between Kp and Kc needs some consideration also. Kp is equal to Kc times RT raised to the delta N value. Well, R is 0.08206 constants, the universal gas constant for gases, liter, atmospheres over mole, Kelvin. Temperature is in Kelvin. Delta N is equal to the change in molar volumes. When you look at this equation up here, CS2 plus 4H2, that's 5 molar volumes here. And on the product side, we have 1 molar volume of CH4 and 2 molar volumes of H2S, 3 molar volumes. A molar volume, as you recall from Chem 1, hopefully, is the volume occupied by 1 mole of any gas. It doesn't matter what the gas is, it is a volume. Now, the only time you can put numbers to that is if you specify temperature pressure. Like at 0 degrees in 1 atmosphere, you can say 22.4 liters. But you can't say it at 25. It goes up to a higher volume. Or below the 0 degrees, you would have a lower volume. So we just use a change in molar volume in a general context when we talk about this type of problem. So delta N in the problem above would be 3 molar volumes minus 5 molar volumes, which is give you a -2. It has a decrease in 2 molar volumes, and you assume N to be -2. And that's what you place in that expression. And R is a constant, as published on your reference sheets. Kelvin is, of course, degrees C plus 273. And then you plug in and get a number. Okay? Regardless of the units, irrelevant. Because this is just a relationship. Now, Kp and Kc can be, can be changed in their positions, like Kc equals Kp, but Rt goes to a minus delta N value. Now, you may have a minus in here, but what you would do, if this would give you a -2, which goes to a +2. So you want to be careful depending on the expression. If you have a Kc equals Kp Rt minus delta N, you have to put in the delta N. Be sure it's the change the negative is applied to the change. Up here, you just put in this case, just a -2, and of course, it's still positive in that context. And then they give you a Kc value, and you plug it in, punch it in your calculator. Let's see if we got one in here. I think we got one down here somewhere. Yeah, 1451. So your reaction is CS2 gas plus 4H2 as a gas, equilibrium with methane gas and hydrogen sulfide gas. And the Kc value for this reaction is 0.28. What is the Kp value? Kp is unknown here. Well, the expression for Kp, as I've shown you, is the positive value of delta N. I used to think of it to keep them separated, like if I had a Kc and Kp and I needed to be sure about the expressions, P is positive. So that means when I write this, KCRT, I'm going to use a positive delta N. If I use a Kc equals Kp, that's not a P out there in front, so RT minus delta N is what I would use. So it's just a memory device for me. The P refers to positive delta N value. And then the other way, it looks the same except you put a negative on the delta N value. So that's just a little help hint in the type of problem. I'm going to get rid of that and recover the space. So in the issue of this one, let me be sure I've gotten all the data. I did. Okay, the temperature is given to be 900 Celsius, and we want to add 1173 Kelvin. The Kc value is up here, 0.28. R value is still 0.08206 liter atmospheres over mole Kelvin, but you can drop the units out of this thing. So Kp now is equal to 0.28 times 0.08206 times 1173, and the change in molar volumes This is 3 VM, and this is 5 VM. So between these two, we have a delta N equals a minus 2. So that's what you have to put up here, is a plus a minus 2, because this was the KP expression. Okay, so punch it in the calculator and plug and chug, so to speak.
Professor. Professor.
Okay, now,
Professor, I have a question for the temperature.
just to add to the notations here, 0.08206, this is a reciprocal function like this. And just to emphasize the issue here, and I got 3.02 times 10 to the minus 5 is the value for your KP. Of course, you can see that it's significantly different from the KC expression. But the idea of it is they mean the same thing in terms of magnitude defines, well, it ain't got many products. You got a lot of reactants left at equilibrium when it's formed. So that's the point I want to make, along with how to substitute those values. Okay, so you're given an equation, and it has a Kc value with it. Okay, the Kc expression is NO gas. Everything's gas phase. I'm going to save myself some time here. Divided by NOBr squared. And that expression is, in fact, equal to 3.07 times 10 to the minus 4. Everybody understand that? We're good? All right. The question is, what if whatever got this number, the concentration values do not give Kc equal 3.07 times 10 to the minus 4. What does that tell them? It says that the equilibrium is not stable. And will shift to establish a new equilibrium. Shift left, I'll say that, left or right, depending on considerations, to establish a new equilibrium. Now, let's say you were given values that did not add up to or calculate to be the equilibrium constant. What it is called is a QC value. If concentrations in equilibrium expression does not equal Kc, then it is a QC value. So that when I write the expression called the QC value, it's written the same way, but the numbers that you plug in will not give you this Kc number here. QC is therefore NO squared, I scribble it out, Br2 over, their own molar. So they're the same type of notation, but if I plug in the givens, say in a problem, it doesn't equal the Kc value. And so we call it a QC. Well, here's some problems where they don't give you you can see in your sheet, where they don't give you, they give you numbers. If you plugged them in, they wouldn't give you the Kc value. Well, based on that, you can decide which way it's going to shift. And this is how you. Okay, so we're going to determine the direction the reaction is going to shift if you plug in numbers and it does not equal the Kc expression, a value. Now listen to me carefully. I'm going to ask a simple question. K versus Q. Who comes first in the alphabet? K. That's a no-brainer. But what I want you to do is I want you to put K first, I'll show you, and then Q second. That's 3 times, KC, KC, and KC, and on the right, QC, QC, and QC, just as I've written it, like this. And between these, you are to put inequalities left, where KC is less than QC, and an inequality pointing to the right, where QC is less than KC. In the middle one, place it equal. Now what it tells you when you compare the QC number that you calculate with the KC number that's given is which way it's going to shift. And the reason I set it up like this is because the inequality symbols point in the direction it's going to shift. Now the textbook, if you looked it up in the textbook, they always give QC first. And students get confused. But if you do this, just look at the inequality for reactants going to products. It's going to, well, I'll do it like this. If this is the condition, you have the reaction will proceed to the left. Shifts left. In the middle, it will be at equilibrium. If that happens to be after you substitute QC equals KC. And in this last case, it shifts right in the direction of the inequality points. Now this will show up again when we get to KSP in the next sections. So, it's a real simple process now, if you understand that. These are the conditions that define the direction of shift. So, we go back and we say we're given 2NOBr as a gas. I better put it in just in case. As a gas. And goes 2NO as a gas plus Br2 as a gas. And Kc is given to equal 3.07 times 10 to the minus 4. Now that equals NO squared Br2 to the first power divided by 2, NOBr raised to the second power. Okay. Now, what we want to do is call this a QC number, NO squared Br2 over NOBr squared, and substitute the givens. Let's say you're given the data that shows up in here. If your NOBr is 0.072 molar, NO is 0.012 molar, and Br2 is 0.123 molar, what's the QC value? So we substitute those into that expression, 0.0720, that one squared, and 0.162, 2 molar, That one's squared also, and the bromine is 0.123. 3 molar. And we get a number. So I pick up my values off of the worksheet and put them in here, solve for QC, and I get this number for QC. Now I write the KC first, QC second, and then put my inequality in. Well, the inequality points to the left. So this indicates reaction under the conditions that are in that set of data shifts left. And that's the long and the short of that story. If you set up K's before Q's, it's real easy to point them out. And they got about 3 or 4 more in there, and you just do the same thing. Now, again, if Q equals KC, well, you're at that equilibrium. If it turns around where KC is greater than QC, then it's going to shift to produce more products in the reaction. And the next one's same idea. Plug in the numbers and compare KC, it gives you KC, plug in the values of concentration and see who's bigger or smaller. Look at the inequality, and if it points left, it shifts left, and points right, it shifts right, provided you set up K before Q to make your comparison. Initially, a mixture contains mixture with no equilibrium. That's just like the initial. I think you can handle the rest of it. Le Chatelier's principle. That's the biggie.